Okay, well, let's make a start. Good morning to those of you in Europe and Africa. Good afternoon and evening to those of you joining us from Asia, and a very warm welcome to you all. Thank you for joining this, the 20th of our regular series of seminars on pumping topics. This one will last about 40 minutes, allowing us time for a Q&A session after the presentation. Share the screen. Okay. So here is a listing of the previous short courses we've run during the last year. If you've missed any of them, you can get a copy of the materials from our website. Use the following link, shortcourses@ruhrpumpen.com, or go to ruhrpumpen.com and click on the link to RP short courses. If you go to ruhrpumpen.com, you get to this screen, and here is the link to the RP short courses. If you click on that link, it takes you to this screen here, which you can also access directly by this address. You'll see all the courses listed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Most of the 19 courses are up there. I think 18, the last count. We don't like to put them up too soon after the live presentation, or people won't bother to attend and will just download the presentations later. This spoils the value of a live Q&A session, which is actually my favorite part of these sessions. Here's what we'll be covering today. We'll start with a presentation on VS1 and VS6 pumps, which are among the least well understood pump types among rotating equipment engineers. And this is because you guys don't see them nearly as often as horizontal pumps. So we'll revisit the VS6 and VS1 pumps, and then I will go on to introduce an exciting new development that we're bringing to this market. As usual, we'll be holding a Q&A session at the end, so please use the Q&A facility at the bottom of your screen to ask any questions or to make any comments. I'll address those that I can live at the end of the session, and the rest we'll address by email in the coming days. We are recording this session, and we will make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow and of the Q&A summary from both of today's sessions. So that's what we're looking at. VS6 pumps, defined by API 610 as double casing, diffuser type, vertical suspended, often called canned suction pumps or vertical barrel pumps. Traditionally, they're used when you have very low or even zero NPSH available at grade. It works on the basis that if you have 0 NPSH available here, then 3 meters down, for example, you have 3 meters of NPSH available. So you're increasing the NPSH available for the pump to be able to pump. And we make the pump long enough by putting in spool pieces, 1 meter sections of pipe and line shaft. We put in as many spool pieces as you need to position the first impeller low enough to give you the NPSH margin you require, normally a 1 meter margin. But it's not just an NPSH saver, it's a space saver too. It takes up around 20% of the floor area of the equivalent BB2 pump. And it's a cost saver too. Less expensive than the equivalent BB2, and it only has one seal and one sealing system. But civil engineers don't like digging holes. There can be good reasons, such as water tables and groundwater quality, but if you can persuade them to do so, then you're saving all the way. The big users of these pumps: light hydrocarbons, C2, C3, C4, condensate water in power stations, ammonia pumps, liquid oxygen, liquid nitrogen, cryogenic pumps. They're available both in API 610 build and non-API, Hydraulic Institute standard. You'll come across two different styles of VS6 pumps. The radial design on the left here, which is primarily of European design, and the Francis vane on the right, which is predominantly of American origin. The American design was a spin-off from borehole pumps, which are widely used across the Americas. Now, with borehole installations, you're trying to get as much water as possible out of as small a diameter well as possible, and you're looking to maximize efficiency. The length of the pump, length of the bowl assembly, the number of stages is not an issue. Hence the Francis vane. High capacity, small diameter, high efficiency, lower head per stage. European manufacturers were not big in borehole pumps. We have plenty of surface water in Western and Northern Europe, so VS6 pumps were developed from horizontal process pumps rather than from borehole designs. So they became radial designs. They tend to be shorter, fewer stages, and bigger diameter than their American counterparts. Also, they have flatter curves, being radial impellers, about a 25% head rise, compared with about a 40% head rise to shut off on Francis vane. Ruhrpumpen has both designs available. Our German heritage pump in the radial range, and our American Byron-Jackson heritage design in the Francis vane. So we can offer the best fit for any given situation. Here's the range chart for the semi-engineered or modularized range, up to about 1,000 cubic meters an hour at 850 meters head at 50 hertz, or at 60 hertz, 5,000 gallons a minute and 4,000 feet head. We have 21 pump models and 55 hydraulics. Most sizes have 2 or more different impellers, for example, a low, medium, and high flow, which means we can always change the impeller combination to maximize the efficiency. And this is also great for retrofitting, should there be a change of duty in future years. But we don't just have the pre-engineered, the modularized versions, we have engineered versions. And here we have some very big mixed flow pumps. I mean, here are some there up in the 250,000 gallons a minute. What are we talking? Nearly 100,000 cubic meters per hour. Pumps are available with above ground suction, like this, or below ground suction. It depends how the user is running his pipework. Process pumps are almost always above ground. Below ground tends to be used more in water service. Now, in establishing the NPSH available, you specifying engineers need to think a little when you calculate your system NPSH. You frequently tell us on the data sheets the NPSH available at the center line of the suction here, which means you're assuming a value for this dimension. It's better that you give us the NPSH available at grade at this point, and we will calculate the required length to put the first stage impeller at to give you the margin you require, the NPSH margin. With the below ground suction, we do want you to tell us the NPSH available at the suction flange, because you know where that is. That's a positive location. We then will calculate the length required to give you the NPSH margin required. Mounting options, there are 4 of them. First one, the square mounting flange on the barrel, this one, is set directly on prepared foundations. So there's your square mounting flange here of the barrel. That will be set on directly on the prepared foundations. Number 2, we supply a square sole plate, which is set in the foundation when it is poured, and the square barrel flange sits on top of that. Third option would be a steel channel frame, a base plate effectively, and again it is set into the foundation when it's poured, and the square mounting flange sits on top of that. And the fourth option is a separate mounting flange. This was a requirement of API 610 8th edition, and it allowed for through bolting for the head and barrel flange rather than captive bolts as shown here. This is no longer a requirement of API, but is frequently, well, many pump specs have that left in there as a hangover from 8th edition. They haven't really updated it. The pump comes in API version and non-API version. The non-API, which is usually in water service, will probably have threaded cast iron bowls, although it can have flanged steel bowls. It will also have integral wear rings, and the impellers will be secured by taper lock bushes. The API build will have flanged bowls, replaceable case and impeller wear rings, and keyed impellers. Some vendors, raw pumping included, use a low NPSH first stage impeller to shorten the pump as much as possible. This specially designed first stage has been designed to have a wide operating range while maintaining good NPSH performance. Others will use an inducer to do the same thing. How well this works depends on the design of the inducer. Historically, inducers had a U-shaped NPSH curve, which limited the operating range. More recent designs, like these by Elliott Cryodynamics, they have a broader range right across the full working range of the pump. The oil and gas industry is very suspicious of inducers, and many specs still forbid them. Here are the main features of an API build VS6 pump. So it will have, the fabrications will all be to ASME Section 8 and will have code certified welding. It will have weld neck flanges, full penetration welds, which allows you to carry out radiography or LPE, MPE of the welds. May well have a surface mounting flange left over from the 8th edition requirement. It will certainly have split ring and key impeller mounting, flanged bowls, separate impeller and case wearings. A note here on the API material codes. A lot of pumps in light hydrocarbon service, C3, C4, propane, butane, these have historically been supplied in S1 materials. For a VS6 pump, that means steel pressure boundary, but cast iron bowls and cast iron impellers. 12th edition has got rid of S1 as a material, so S5, steel bowls and impellers, is now the minimum standard to be fully compliant with API 610. But that doesn't mean that cast iron bowls and impellers aren't really suitable still for propane and butane service, for example. Here are some more features on the left and the corresponding benefits on the right. I won't bother to read the slide. I'll leave it up on the screen for a little while and let you read it for yourselves. And here are some of the differences between the European, the radial, and the American Francis vane designs. In the European design, tie bolts are most commonly applied, and when lengthening the pump for NPSH reasons, they usually lower just the first stage rather than the entire rotating element. And as European motors seldom accommodate thrust, the thrust bearing is built into the standard pump. Looking now at the commercial VLT, the non-API pump. It has cost savings built in for this less arduous and hazardous service pump. So we'll have slip-on flanges, integral wearings, and collet-mounted impellers, for example. It's commonly used in condensate water service, but it's perfectly suitable for hydrocarbon surface as long as API 610 is not specified. It'll give you cost savings of about 25% over an API pump. Looking a little more detail at collet-mounted impellers versus split ring and key. So collet-mounted impellers drive this taper collet into the bore on the impeller. And it's easy for assembly and disassembly, positively ensures the positioning of the impeller, and it's lower cost than the alternative, which is the ring and key, split ring and key, which offers the advantages of being an absolutely positive retention, and it's less susceptible to loosening when subject to shock load. So that's the requirement, a requirement of API 610. And now we'll look at integral wearings versus renewable wearings. Now, you always have renewable wearings on an API pump by code. But on our non-API offering, we encourage integral wearings, or integral wearings initially when you buy the pump as a new pump. When the first major overhaul occurs, which is probably 5 years down the line, you machine and fit bowl wearings at that time. Then at the second major overhaul, probably at about 10 years, you machine and fit impeller wearings. Now, technically on an API pump, you could have integral wearings because Per API, you only need to have provision to fit replaceable wear rings in the future. So you could choose integral wear rings and do the same retrofit later. But in practice, nearly every spec specifies that you shall have renewable wear rings on the new pump. Looking now at the nozzle head, well, being a fabrication, we can design and build it pretty much any way you want or specify. So 300-pound flanges, 600-pound, 900-pound. It could be designed rated for the suction pressure with only the discharge area rated for discharge pressure, or the whole fabrication can be rated for full discharge. The barrel on the API pump has an elliptical end, which allows us to put a full penetration weld here at the bottom. The non-API version uses a flat plate bottom as standard with a fillet weld. It's a cost-saving exercise on these low-pressure pumps. Looking at the column pipe, here we're looking at the end of a column section. And what you see is the bearing spider, which is integrally welded and machined at the same time as the column flange. And this ensures perfect alignment, which is very important when a pump can easily be 30 feet long and running at 3,600 RPM. The sealing options. The API version has seal chambers suitable for API 682 seals. VS6 pumps most commonly have a single seal with a Plan 13 sealing system, which is a flush from the seal chamber back to suction. They frequently have tandem dual unpressurized seals, which will use Plans 13 and 52. And double seals, dual pressurized seals, will use Plan 53A or 53B. Now, we prefer to have seal systems, Plan 52 and 53 seal systems, mounted on their own support stand. This sort of cantilevered load off the side of the pump is not good for nozzle loading or for vibration, but we can do it, especially on the larger pumps, as shown here. This larger pump, a much more substantial fabrication, can take this cantilevered load. So as I said, Plan 13 is usual for a VS6 pump. The seal chamber at this point sees discharge pressure, which is broken down by this throat bushing and the Plan 13 orifice, so that the pressure in here is at about suction pressure plus 25% of differential pressure. Now, if this doesn't provide sufficient vapor pressure margin, then adding a Plan 11 will raise the seal chamber pressure and ensure vaporization doesn't occur between the seal faces. So Plan 11 plus Plan 13 equals Plan 14. The arithmetic's a bit dodgy there, isn't it? But never mind. Most commonly, this will be required in very low head pumps, which aren't generating much differential pressure. On the non-API pump, the base design is with no specific seal chamber. The single seal is set in the pump discharge flow, which lubricates and cools the seal faces. The seal sees full discharge pressure in this configuration and needs no seal flush piping. But seal chambers and seal flush piping are available when requested, and of course are needed if you're going to fit tandem or double seals. Here is the Plan 52. It's used on tandem or dual unpressurized seals. You will have a plan 13 on the inboard seal, and the plan 52 provides a flush to the outboard seal, which will sweep away any leakage past the inboard seal. Now, if this leakage is in the liquid phase, the level in the reservoir will gradually raise and it will trigger an alarm. If the leakage, on the other hand, is in the vapor phase, as it might be on an ethane or propane pump, then the pressure in the vessel will rise and trigger an alarm. Commonly supplied also would be a double seal with plan 53, plan 53A in this instance, like a plan 52, but this time it's pressurized with nitrogen. The barrier fluid lubricates and flushes both the inboard and the outboard seals. So leakage is therefore either into the pump or out to atmosphere. Barrier fluid must be compatible with the process fluid and it must be non-hazardous. Any seal leakage will trigger a low-level alarm. Now, in higher pressure systems, there is a risk of dissolving nitrogen in the barrier fluid, which might bubble out between the faces. So for higher pressures, an accumulator or bladder tank is used, so the nitrogen is not in direct contact with the barrier fluid. An external cooler is used instead of cooling coils in the vessel. Single seals with a plan 13 often have a dry running gas seal as a backup, with plan 75 or 76 to detect any leakage past the inboard seal. Here we're showing the plan 76, which detects seal leakage in the vapor phase by means of a pressure transmitter in the vapor collection system. So this would be common in, say, a propane pump or an ethane pump. It's plan 76. Plan 75 detects seal leakage in the liquid phase by means of a collection pot and level transmitter. So this would be more practical in, say, a butane pump, where any leakage would be in the liquid phase. You can also have a plan 72 used with dry running gas backup seal, of course, and it flushes the space between the primary and backup seals, reduces fugitive emissions, and prevents icing in cold pumps. It would usually be used with a 75 or 76 to detect the primary seal failure. I mentioned earlier that the base design for the American designed VS6 is with thrust taken in the motor. But most European and Asian motor suppliers don't have this construction as standard, so we have an optional construction with a thrust bearing in the pump. Here's a grease lubricated bearing used on the smaller sizes. You'll see it sits on top of the mechanical seal flange, like this, and like this. For the larger pumps, we have an oil lubricated bearing built into the motor stand, like this, and as shown here. There's the thrust pot, and here. Now moving on to the new development, as I promised. The new development for us is a QuickShip VLT. Now, quite a few suppliers have a QuickShip offering, so you might well be forgiven for saying, what's so special here? But this one is more comprehensive than anything else on the market. Most offer little more than a QuickShip bowl assembly, but the Röhrpumpen QuickShip gives you a fully compliant API 610 12th edition pump set. It's built as a semi-engineered package with limited but still extensive options. It's for the full range, 21 pump sizes, 35 hydraulics, up to 1,000 cubic meters an hour and 850 meters head at 50 hertz, or 5,000 gallons, 4,000 feet at 60 hertz. Delivery time is 18 weeks for a complete pump. That's ex works after receipt of order. This is a conservative promise of 18 weeks. We are actually planning to do it in the future in 15 weeks, but we're starting the program off with 18 weeks to be safe. And a bowl assembly would be 8 weeks. Here's the basic build. Dual certified WCB, LCB bowls, making them suitable for low temperature use as standard. You'll note duplex stainless steel impellers as standard. A lot of options here for the nozzle head. You can have single or double seals. Various seal flush options. Seal pots. 150-pound or 300-pound flanges. Performance testing is non-witnessed only. Paint system, shock blast and Amalock 2 self-priming epoxy paint finish. MTRs. And this is an important one, non-standard head or barrel dimensions, which means we can match existing installations. Come in, or we could supply them in left-hand and right-hand pumps, for example. This one's quite a big deal. It's a big advantage over other pump vendors in the market. Motors. The setup here is around American motor suppliers and specifications. I'll address this some more in just a minute. The documentation is limited but fairly extensive. I think you will you'll agree. So that's what you do get with the quick ship package. This is what you don't get. You don't get a bespoke documentation package. You get just these fairly extensive but limited documentation. You don't get any witnessed or observed testing. And this because we might carry out the testing on a Saturday or on second shift. We might rearrange testing time at little or no notice. So there really is no possibility in an 18-week delivery window to give you advance warning of a date for even an observed test, never mind a witness test. So no witnessed or observed testing in the quick ship program. Similarly, no NDE. No time for it in an 18-week delivery time. We don't accept customer specifications with the purchase order. Now, at proposal stage, these will be reviewed, commented, and agreed, and a detailed scope of supply. So an agreed scope of supply. That can appear in the purchase order, but that will be it. It must be a standalone document. We won't be re-reviewing at manufacturing stage specifications. It will just be meeting the agreed scope of supply in the PO document. You won't get a dedicated project manager. Your project manager will probably have a couple of them for the whole scheme, and they'll have something like 50 other jobs. So they won't be giving you the individual attention that you get with a long lead time pump, a standard pump. But the important thing is all of these are available, just not within the quickship program. So if you can live with 36 weeks for a pump, then you can have all the options you like. You can have all the NDE you like. You can get all the documentation you like, just not within the quickship program. Now, these limitations then they make this quickship program more applicable to end user purchasers than to EPC contractors. You EPC contractors are usually constrained by project specs and project requirements, especially on documentation and inspection. Well, this program has been rolled out initially predominantly for the North American market. For Europe, Middle East, Africa, and Asia, it will need some tweaking. For example, it doesn't currently allow for European and Asian IEC designed supply motors, doesn't allow for separate thrust pots, it doesn't allow for flanged and welded seal piping, and there may be other essential European, Middle East, Africa, and Asia requirements that we haven't necessarily thought of. So that's down to you to tell us what is an essential thing that should be in a quickship program to make it usable for you. If the demand is there, then the program will be expanded to suit this Europe, Middle East, Africa, and Asia market. Now for the non-API build pumps, the Hydraulics Institute compliant pump. Not dissimilar to the API offering, the same pump sizes and hydraulics and materials, just a few less options. The same 18-week delivery time or 8 weeks for a bowl assembly, and in the future, getting that down to 15 weeks. Here's the detail. You'll see ductile iron is an additional material to the WCM LCB dual certified bowls. The wear rings are not included in the base price, but they are available as an option. The same discharge head options with an option on, the standard is with slip-on flanges to keep the price down, but there's an option for full penetration welds, bringing you closer to an API build pump. The same epoxy paint finish, the same testing options, and the same non-standard head or barrel dimensions, which allow you to go with left-hand or right-hand pumps, and also to match existing installations. The documentation, not so comprehensive as the API package, but I think par for the course for this commercial pump. Well, there we go. That pretty much concludes the fun for today. Here is where I normally get to advertise the next of the short courses, but at this moment, I don't know what it's going to be. I have several ideas, maybe magnetic drive pumps, maybe cryogenic pumps, one or two other ideas floating around in our corporate heads at the moment. We'll advertise in due course, but the next course will be on Thursday, the 2nd of March, which is in 4 weeks' time. I'm leaving this meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer here and now, but those that need a fuller answer will be answered within a few days. Anything that you think of later, email it to info@shortcourses.ruhrpumpen.com. Our marketing team are standing by to direct your questions or suggestions to the best person to answer them, and they'll be sending you the YouTube recording and PDF of the presentation. If you need a certificate of attendance, a certificate of completion for this short course, again, info@shortcourses.ruhrpumpen.com. And here, right at the end, are 8 slides about Rohrpumpen that remind you of who we are and what we do. They'll be in the PDF copy of the presentation, so you can peruse them at your leisure. I won't bore you with them. Now it's more important that we get on with the Q&A. So let me stop the share and let's have a look and see what has been said. Here we go. First, we've got quite a few questions, 17 of them here it looks like. What's the maximum range of CEP supplied so far in the world and by Mrs. Rohrpumpen? Some of the deepest pumps, I've come across pumps that are as deep as 1,200 feet. We have some designs, let me put it this way. On a long pump, shaft stretch becomes a concern. As the pump stretches, just under the weight of the bolts and impellers, the impellers and the shafting can stretch the pump, and so you need special designs with long wearings. Instead of that wearings might normally be about that size, they suddenly need to be this size to allow for that stretch of the shaft. And we do have some designs that have gone down to 1,200 feet, I think. But I need to look into it. We regularly supply these pumps, say, as fire pumps on offshore platforms, and then they would be easily 30 to 40 meters long. I'll get you a better answer to that one, Rajiv. Rajiv Jain again says, is it mandatory that all the non-API pumps are having threaded bowls? No. We've got it available with threaded or with flanged bowls. The cast iron bowls will be threaded, but any other materials will have flanged bowls available. An anonymous attendee has said, will the flow range of a VS6 pump be able to handle down to 15% of BEP? Pretty much, yes, 15% of BEP is pretty much where the minimum flow would be on this type of pump. But we would always look at it, specifically application by application. But yes, in general, a VS6 pump will operate down to about 15% of BEP flow. Ashish Patel says, on slide 18, standard design mounting plate, the question is this mounting plate welded to the pump can? Yes, on the standard design, I wonder if we can go back to that. Let's have a look. Sorry, while I'm scrolling. There we go. Best seen here in this here. This is the mounting flange, and it is welded. It is the top flange of the suction can. There it is there. And in the separate mounting flange, this flange is, yes, welded to the barrel. Rakesh Chowdhury says, are there allowable nozzle loads applicable with the water service canned pumps with suction nozzle on the can underground? If not, how the piping loads can be taken? It follows the API nozzle loads. But you should always well support your suction piping. It should be the piping that is designed to minimize these nozzle loads, but it does allow for API nozzle loads. Ashish Patel, question on construction. Can VLT pump be steam traced? This question is mainly to application of fluid, which is congealing in nature and having very low NPSH available. Yes, there's no reason why we couldn't design the pump with heat tracing. Yes. Mayo Barahate says, what will be the nozzle loads on the underground suction VS6 pump? Will it be 0 or some positive loads? Okay, it's, as I just answered, it will be per API 610. Rajiv Jain, what kind of lubrication followed for bearing? Okay, the line shaft bearings and the ball bearings are product lubricated. They're a sleeve bearing. They're made of carbon. They're carbon bearings. For the thrust bearings, in a thrust bearing, if you have a separate thrust bearing, then they would either be grease lubricated on the smallest sizes, or on the larger sizes, they would be oil lubricated. Rajiv Jain says, as you are not providing witness, are you showing performance at site? Absolutely. The API pumps are always performance tested at the rated duty point. Also, the commercial VLT, the non-API version, can have an option of a performance test, again, which will be at the rated point and the results will be provided to you. It just can't be witnessed, that's all. Mohammed Ibrahim says, usually the first impeller of VS6 pumps has a lower number of vanes compared with the series impellers. What is the reason for that? The number of vanes, or the design of the first stage impeller, is optimized for the lowest possible NPSH available. Sometimes it will have fewer vanes, sometimes not. It will depend on the hydraulic design. There's no specific reason why it would have fewer vanes, just a matter of optimizing the flow pattern through the impeller. Rizal Ibn Wahid says, I have a question. How VS6 prevent waxy occurrence in pumping liquid, considering limitation in power supply and no space for additional utility requirement for heating jacket? Waxy occurrence sometimes occurs in lightweight hydrocarbons. Is it recommended VS6 to handle lightweight hydrocarbon with intermittent operation? In many cases, when the pump is shut down, there are some light hydrocarbons inside the can and can become waxy when temperature is decreased. I might get a more complete answer for you for that, but yes, there is no reason why you cannot apply a steam jacket around the outside of the pump, or trace heating around the outside of the pump if you're concerned about wax formation. Rakesh Chowdhury says, what is the recommended arrangement and available options for sealing the barrel and can at grade level? We would frequently, if there is concern about surface water and possibly floating the barrel out, we have supplied frequently with a gasket between the mounting flange and the foundation, especially with a sole plate set in the foundation. So a gasket can be supplied there. A drain can be fitted into that annulus between the barrel and the foundation as well. Ahmed Badawi says, can you please provide some explanation about the gas coffer dam maybe? Ahmed Badawi, I don't fully understand your question. Perhaps you could phrase it in a different way and I'll look at it. Khalid Shamam says, you mentioned 900-pound flanges. Can we get an inlet pressure as high as 150 bar? It would be a specially engineered pump, but yes, we could handle 150 bar suction pressure. Anonymous attendee has said, please advise on how will be the maintenance procedure for these type of pumps. Well, most of the maintenance will be on mechanical seals. You shouldn't have to take the pump out for 2 to 5 years as standard. So when you have to do that, you do have to pull the whole bowl assembly out of the pump and take it off to the workshop for that. But that should be really only every 3 to 5 years. Routine maintenance would all be on the mechanical seal or thrust bearing, which is mounted up in the air where it's accessible. Shyam Kumar says, hi, how do you support interconnected piping in case of off-skid seal system to pump, if it's more than 1 meter apart, which it might well be. This would normally be field run. We would often supply you with lengths of pipe or tubing for it to be field run. So yeah, it's run in the field. It's Anders Moller says, for the quickship pumps regarding the no NDE, does this exclude hydrostatic pressure test of the bolt? No, absolutely. You do get a hydro test as standard. And 2, no material certificates to the customer. Material certificates will be supplied. Yes, we can supply you with material certificates for the bowls and for the pressure boundary. An anonymous attendee has said, I hope your next session will be about cryogenic pumps. We'll see what we can do. It's certainly one of the options we're considering. Ahid Prihanta says, sir, I have a question for use in seawater. Could you recommend the material, since even in API 610 is not mentioning for seawater use? Yes, I mean, historically, nickel aluminium bronze has been a popular material for seawater services. It's a very good material and has been used for many years. It's easy to cast and easy to machine. More recently, duplex stainless steels have been specified, and even super duplex stainless steels, and they work fine. We have no selection bias towards that. We'll do it in whichever materials your metallurgists say you need. So typically, though, nickel aluminium bronze has worked very well for many years, duplex stainless steels, and increasingly super duplex. Girish Palo says, selection criteria for OH2 pumps versus VS6 pumps for hydrocarbon service. When to select which type of pump? That's a nice question. OH2 pumps will generally be less expensive than a VS6 pump. So you would normally go with an OH2 pump and only switch to a VS6 pump when you have an NPSH problem, if you cannot manage with that. When it comes to a BB2 pump will be more expensive than a VS6 pump. So a VS6 pump is a real option against a BB2 pump. But your question was about OH2 pump. Generally, that would be a more acceptable solution than a VS6 pump, unless you have an NPSH problem. Suharto has said, what is the maximum length of the barrel and can? Practically, there isn't one. I'll have to check and see what the longest one we've made is, but they would regularly be 30 feet, so 10 meters long, quite regularly. Khaled Hamam says, we are looking for a seawater injection pump with an inlet pressure of 80 to 150 bar and discharge pressure of 200 bar and a flow rate of 1,000 cubic meters per day. Do you have such a solution? Yes, I'll contact your local Royal Pump and salesman, and he will be able to offer you a pump for that. A seawater injection pump, that would be probably a horizontal multi-stage pump a BB3 or possibly a BB5 type of pump. Anonymous attendee has asked, what are the causes for frequent eccentricity issues seen in the stuffing box bore in VS6 pumps? If you buy a cheap pump, you might end up with that, but you won't if you buy it from a reputable supplier such as Ruhrpumpen or indeed Flowserve or Sulzer. There are many good suppliers. If you've got a good design with a rabbited fit, a register fit of the stuffing box, mechanical seal chamber inside the pump, then you should not get an eccentricity issue. Yarash Palo says, any torsional and lateral analysis for these pumps? Absolutely yes, but not within the QuickShip program. But yes, absolutely. Lateral and torsional critical speed analysis is an option you can have. Anonymous attendee, good morning and thank you for the presentation. I'd like to review some of the operational philosophy on vertical pumps, pros and cons, on, off or on VFD with continuous and variable speed. Yeah, increasingly variable frequency drives are being used on the pumps, and vertical pumps are very suitable for those. We always would do a torsional and lateral critical speed analysis and indeed a natural resonant frequency test on pumps that are using a VFD. Fatima says, why is it that vertical pumps, the German ones, have stable curves, but US designs have steep curves, high rise to shut off? I would take issue with you saying it's a stable curve as opposed to a steep curve. The two things are not mutually exclusive. A head rise of 25% is representative of a low specific speed, a radial design, and a mixed flow design, a Francis vane design with a medium specific speed will have a steeper curve. In a previous presentation, I have talked about shapes of curves and whether they are the benefits of a steep curve over a flat curve. The real benefit of a steep curve is that it's much more controllable. A small change in flow is accompanied by a large change in head, or more to the point, you get a small change in head, you get a small change in flow with a steep curve. With a flat curve, you can have a very small change in your system head, and it can be quite a wide change in the flow rate. So there are advantages, more advantages in my opinion, to a steep curve than there are having a flat curve. But if you look at one of my previous ones, I've looked at curve shape in that presentation. Mohammed Samir Gouda says, assembly of wearing and clearance methods. I don't fully understand the question. When we assemble the wearings on the pump, obviously the clearances are checked at that time. If it's being done as a retrofit, fitting them later on to a pump, then full dimensional information is provided to your machine shop so that you can provide the correct clearances. Pushpak Akade says, is API complied QuickShip delivery with gearbox driven pump possible? Not within the QuickShip program. Gearboxes haven't been considered for the QuickShip program. There's not really a great deal of demand for that, so it's you'd be on a standard pump delivery. Shyam Kumar says, is it necessary to fix the pump with anchor bolt, or can it be pipe supported? Yeah, it should be bolted down, definitely. These are big pumps. They're not like vertical inline pumps, which are frequently floating within the pipework. Rajiv Jain says, thank you, Mr. Simon, great presentation, answers to my queries. Oh, thank you, Rajiv. Thank you for your comment. Rakesh Chowdhury, how can the can be drained for rotor maintenance apart from a draining tube inside the can with external pumping? Yes, we very frequently supply a dip tube inside the can, and that is drained either by pressurizing it or by having an external pump to suck it clear. We can also fit external drains on the pump, like coming from the bottom of the barrel round and up to the surface. These are options that can be done. Fatkur Rahman says, just info. Oh, sorry. Okay, moving on. Mayo Barahate says, which materials for VS6 pumps recommended for the water, which has, I guess, reverse osmosis, reject water with too high in chlorides, say 25 milligrams per litre? We're not metallurgists, we don't specify materials, but from my experience, I would have said, in this instance, you would be looking at a duplex or super duplex pump. Jerome Boll, how is the pump itself sealed on top of the can? Okay, standard is no sealing there, but we can put a gasket in there if you're worried about groundwater rising up through the foundation. Krishan Yadav, which is the better way of draining the suction can, internal or external drain? And how do we do the draining by internal drain? Do we need pressurized nitrogen for draining? My preference is always for an internal drain tube, a dip tube down the pipe. External drain pipes tend to get knocked during installation and dented. So the internal drain, which can be strapped to the side of the pump, banded to the inner pump, that's probably, in my opinion, the best way of doing it. And yes, it's usually done it by pressurizing with nitrogen. So you pressurize the vent connection on the barrel and push it out through the drain connection. Anonymous attendee, how to detect if bush bearings are worn out? Is their diagnosis possible by vibration analysis? You would be measuring with a portable vibration meter on the top of the pump, and you trend monitor, and you would detect gradual increasing in vibration as time goes by, and you would schedule the pump for a strip down. It might be the line shaft bearings, it might be the pump bearings. You probably can't do it just by measuring the vibration on the head plate, but to specifically decide what it is. But you use that as a diagnostic tool to tell you when to schedule a maintenance and a strip down. Shyam Kumar says, what's the major criteria for selecting a VS6 pump? Is it only lower NPSH, lower temperature, or something else? Primarily, it's low NPSH available that demands a VS6 pump. But as I say, if the system would otherwise suggest a BB2 pump, you could well consider a VS6 pump as an option on that. Could be less expensive if you can persuade your civil engineers to dig a hole in the ground. Anonymous attendee, does upward shaft axial movement is common at startup? Good question. Yes, what we would normally get during startup is an initial up thrust, just for less than a second, just a little put up thrust before the pump settles down into down thrust. And thrust bearings are either in the motor or in the pump are designed to take this into account. Shyam Kumar, how can we reduce the shutoff pressure with the same rated impeller, since shutoff pressure is exceeding the downstream limit? You can't. It's simple as that. You could only put a pressure relief valve somewhere in the system to protect yourself from that. There's no magic design that can change the design of the impeller. If it has a steep curve, it has a steep curve. Adnan Safraz says, can we replace the tie rod arrangement with stud and double bolt arrangement to stack the impellers in VS6? That would be a specific question to the supplier of that type of pump. Some suppliers, I mean, in the same way as Rohrpumpen has a European historic design and an American historic design. And we can supply either a tie rod design, or if you don't like a tie rod design, we can supply you with flanged and bolted design. Similarly, I know Flowserve, for example, have exactly the same thing. They have Francis Vane and radial designs, so they could offer you either. But retrofitting it afterwards would probably be a problem. Once you've gone down the line of a short, fat design with tie rods, you can't suddenly put a long, slim design into that same barrel. Anonymous attendee asks, is the seal chamber pressure always throttled close to suction plus 25% on the API version pumps? It will depend what the seal supplier decides he needs, but that is a typical sort of figure. Suction pressure plus 25% of differential will be typical, but it will be whatever the sealed supplier asks us to design for. Ari Virgil1, my apologies if I pronounced it wrong. Per API 610 9.3.8.2.3, for vertical pumps equipped with mechanical seal and integral thrust bearing, which type of coupling type arrangement that Ruhr Pumpen use as API arrangement? Which is most reliable and less expensive? I'd have to look up 9.3.8.2.3, but let me talk in generalities about it. If you've got thrust taken in the motor, then we would fit a rigid 4-piece coupling. And in that 4-piece coupling, you take out the spacer and the mechanical seal then lifts straight out through that gap. If we have a separate thrust bearing, then we would have a flexible spacer coupling, a metastream coupling between the thrust bearing and the pump, and again between the motor and the thrust bearing, and that will allow you to take out the thrust bearing through that gap. And below the thrust bearing, there would be again a spacer coupling through which you can take the mechanical seal. Rizal Ibn Wahid says it's necessary to install the centralizer on the column of a VS1 pump with a length of column more than 15 meters. It would be quite common to do so, to do a centralizer. Certainly, for example, on offshore platforms where these pumps are used as fire pumps or seawater lift pumps, yes, it's quite usual to have sprung wheeled type centralizers to keep the pump steady in the stilling tube in the caisson. Well, that appears to be all the questions. That's not bad. There were 47 questions, I think, here. That was quite good. And we had over 150 participants today, so thank you very much for that. I think it just remains for me to say thank you again for attending today. I've enjoyed thoroughly preparing and presenting it, and especially doing the Q&A. I do love the Q&A sessions in these meetings. So thank you very much for attending, and I hope it was useful. See you at the next one. We'll tell you what it's going to be, and it's likely to be on about the 2nd of March. So thanks a lot, and bye-bye.